Hello everyone, my name is Bilian, coming from Beijing Information Science and Technology University. It's a great pleasure indeed for me to have this opportunity to speak at this meeting. Today, I'd like to present my paper named Collaborative Computing based on Truthful online auction mechanism in Internet of Things. This report is divided into these 5 parts: motivation, system model, algorithm design, experiments, and conclusion. Firstly, I'd like to introduce the motivation of this presentation. With the development of science technology and Internet of Things, many new IoT applications are emerging around us. Most of them are becoming more and more computing intensive and energy hungry, such as virtual reality and augmented reality games. These applications processing requires powerful computing ability and consumes a lot of energy. However, the battery and computing resources on the IoT devices usually are limited. It's impossible for IoT devices to meet the resource requirements of these applications. So, in this case, the low computing ability and small battery capacity are becoming two main drawbacks limiting the development of IoT applications. So, to tackle these two drawbacks, collaborative computing and resource action are proposed as two promising approaches. For the first drawback, it's an effective scheme to allocate resources for IoT devices in MEC system. IoT devices can get powerful computing ability and extend the battery life. For the another drawback, auction mechanism as one of the normal resource allocation form has drawn widespread attention, which can effectively reflect the demand and supply trade-off computing resources and provide satisfactory resources supply. Now I will talk about the system model. An auction uses tracing of MEC's kernel as shown in the figure. Firstly, when a mobile user wishes to rent computing resources to run its deadline-sensitive tasks, it first generates a request and submits the request to the platform. So the platform will periodically collect the state information of each computing node and then publishing it to the mobile users who submit requests. So the mobile user values differently to the edge computing nodes according to the state information. At the same time, the mobile user determines a bid for edge computing nodes. So, based on the request builds and the requests from mobile users, the platform determines the winner of the auction, makes the scheduling decision for the winners, and computes the corresponding payments. Finally, mobile users upload the input data to the edge computing nodes to run their tasks and then pay the corresponding rewards. So, in this page, we will introduce the building language in our auction mechanism. In this system, each IoT device can be considered as an agent to compete for the limited resources. So the agent include multiple IoT devices and a service provider. IoT devices perform as banners, and the service provider acts as sender. As for actions, we explained in detail on the previous page. Our build documentations include the profit of computing this calculation task, the required CPU cycles, and the build value at time slot t. About payoffs, every agent is individual, reasonable, and wants to maximize its payoff. So our optimization goal is to meet the wishes of every participant as much as possible, and to maximizing the benefits of the whole system. Then we give the system model. We divide the system model into 3 parts. They are task model, cost model, and the utility model. In this page, we first introduce the task model. In our optimization problem, we consider the energy consumption as the system's cost, which includes transmission energy consumption, computation energy consumption of a message server, and the computation energy consumption in cloud. Then, summing these 3 kinds of costs, we can get the total cost of the whole system as above. Correspondingly, our utility model as follows. System review includes the utility of IoT devices when the building, and the utility of completing the calculation task for system. Then we have the review of the whole system as shown above. According the above task and cost and the utility models in this page, we give our optimization problem. In our proposed optimization problem, the design variable to be solved are successful building, edge computing, and cloud computation. So the object of our optimization problem is to maximize the time average system review. And there are 4 constraints in our optimization problem. The 1 and the 2 are that the allocated edge computation can not exceed the server's computing ability. And the constraint 3 is that each IoT device's computation task should be completed in only 1 time slot, so they can only win a maximum of 1 build. And the last one constraints guarantees the task queen stability of each IoT device. Part 3, we mainly talk about the algorithm design. Of the first, we have introduced the VCG action mechanism and the strategy for determining the winner can be effectively solved by homogeneous algorithm. So, and then in this part, we save the formulated stochastic optimization problem in 2 steps. There are problem transformation and optimal algorithm design. We first transform the original time average and statistic optimization problem into the deterministic problem in each time slot. And then, for the transformed deterministic optimization problem, we seek to design an optimal algorithm to obtain its optimal. So finally, according to the above two steps, an online algorithm called RMOA is proposed to solve our optimization problem. In this page, we introduce the first step in our algorithm design. We use the near-proof optimization technologies to transform the original time average statistic optimization problem into a deterministic problem in each time slot. And the deterministic problem would be more solvable. So we can also guarantee the near optimality of the transformed problem, and this will be introduced in the next part. Through the first step, the original problem is transformed into a deterministic problem. Then, for the transformed to deterministic optimization problem, we seek to obtain its optimal solutions by introducing language optimization method according to the above two steps. An online algorithm is proposed to solve these two sub-problems. In this page, we give the system review and the quickness of RMOA. For the system review, we can see that the system review's upper bound of our algorithm increase with the increase of V, and by increased V, our algorithm can approach the maximizing system review. In other words, the close to optimal system review can be obtained by our algorithm with a sufficiently large V. For the task quickness, we can see that the time average quickness of our algorithm will always be upper bound. The path for presents our experimental results. In the experiment, we first evaluate the effect of parameters on our algorithm's performance. This page plots the effect of trade-off parameters V on our algorithm. The left picture shows the system review with different V, and the right picture shows the quickness with different V. We can see that with V increases, system review and the quickness both two increases. And there are consistent with the theoretical results divided in the last part. Although the quickness rises with the increase of V, it would always be bounded. In this page, we plot the effect of task arrival rate on our algorithm. We use 3 different colored curves to represent the 3 different task arrival rates. The left picture shows the system review with the different arrival rates, and the right picture shows the queries with the different arrival rates. We can see that with the arrival rates increasing, the system review decreases and the queries increases. What's more, we can see that with different arrival rates, RMOA algorithm can always stabilizing the system review and queries rapidly. It shows that RMOA can be adaptive to the different task arrival rates. In the last, we evaluate the performance of our RMOA algorithm compared with 2 other representative baseline algorithms. They are random allocation and queen-weighted algorithms. For the ratio allocation algorithm, executes the action design in a random way, and queen-weighted algorithm makes action design according to the weighted the task queenness. So the left picture shows the system review with the 3 different algorithms, and the right picture shows the queenness with the 3 different algorithms. We can see that our algorithm can increase the system review effectively, as well as stabilize the queenness at a low level. Finally, is concluding. Firstly, the framework of edge cloud calibration is constructed for resource allocation based on online auction in radio access network. Then, an online and efficient algorithm RMOA is proposed, which can adapt to changeable and unknown task arrival rates and network state, and also can approach the maximum of system review while upper bounding quantum delay. Finally, the experiment results show that RMOA algorithm could increase the system review and effectively and keep a low quality delay at the same time. So that's the end of my presentation today. Thanks for your attention.